Uh, Very good evening to all the participants of this particular meeting or seminar series, which we call as Saturday Manufacturing Talks. It is a great pleasure for me to see that Center of Excellence in Advanced Manufacturing of IIT Kharagpur has really advanced to an extent that the physical facility has almost taken a complete shape despite the constraints due to pandemic. This particular center is now having a very extensive industrial outreach, and so many industrial participants in various forms are collaborating with the center on various state-of-the-art R&D initiatives in manufacturing. This Saturday evening talks where our distinguished alumni are sharing their thoughts and insights on various aspects of advanced manufacturing is a real value addition to this entire set of activities, typically in a period where people are almost confined at their own places and cannot have the kind of physical interaction that we used to have over the years. Today, it is more than a personal privilege for me to welcome Professor Pradip Dutta as a distinguished speaker in this program. Professor Pradip Dutta is such a personality who will not normally need an introduction, and more so, I can understand that in various talks people have to read the CVs to speak about a person, but in his case, being one of his former students and PhD student and master student, and in so many capacities, I do not need anything to read out about Professor Pradip Dutta. But for everything, there is a formal introduction needed, and I would just be very brief about that. Professor Pradip Dutta, of course, is a distinguished alumnus of IIT Kharagpur, and he graduated from our own mechanical engineering department in 1983. Subsequently, he did his masters from IIT Madras and PhD from Columbia University, USA. Of course, he had some industrial exposure in between, but beyond, after graduating, he took up various postdoctoral and scientific assignments, including independent faculty positions in the USA, before he shifted over to IIT Bangalore. And it was around about that time that I also joined as a student of Professor Pradip Dutta way back in 1997. Professor Dutta, it is not a, great surprise that Professor Dutta has been a pioneer in many fields, and he has been duly recognized by virtue of the fellowships of all the National Academies of Science in India, as well as the Indian National Academy of Engineering. He is a fellow of the ASME and various other very respectful award winner, like the Distinguished Alumnus Award from IIT Kharagpur, IIT Madras, and also the Alumni Research Award of IIT Bangalore. It is. These are only just a few, which clearly show that the kind of impact he has in those places from which he himself graduated, including IIT Kharagpur. Professor Dutta has also been a leader in many high impact national level projects, and these are instead of projects, it is better to say these are programs, because these themselves include a large number of very impactful projects. I myself saw him almost single-handedly with the help of my friend and currently a faculty member of IIT Bangalore, Pramod Kumar, to develop a very unique facility, national facility of semi-solid manufacturing processes. Why I am mentioning specifically this is because of this forum of this talk on advanced manufacturing. He has also been a lead professor in the Indo-US research initiative on this clean energy, and various other national and international level initiatives. Professor Dutta has, of course, been an outstanding teacher, and he has been recognized as the distinguished this INA Teacher Award for his teaching activities. Almost all his PhD students who have graduated are either themselves faculty members or very established professionals in their own merit. So today I can understand that Professor Dutta will be speaking about process modeling in manufacturing, one of the very, very important areas, and it will be not an overstatement to say that Professor Dutta has been a pioneer in India to start process modeling in manufacturing. Undoubtedly, manufacturing at some point of time in India was a subject where we had to forcefully include the keyword science to impress upon people that it is really science, because I mean it was more heuristics, more experience than science. Professor Dutta has been one of the pioneers who has brought in deep science and mathematical modeling into manufacturing research. I myself have learned a lot in modeling of this phase change of materials, melting and solidification when I was a student of Professor Dutta. So today we will all be eagerly waiting to listen to the talk of Professor Dutta on various aspects of process modeling in manufacturing. Sir, it is now yours.
Yeah, thank you, Suman, for the wonderful introduction. First, I would like to thank Surjo for inviting me, and also I would like to congratulate him and the other team members at IIT Kharagpur for having established this unique center of excellence in manufacturing. It is something that I think all the alumni will be proud of. Having been in the department, and manufacturing has always been a strong point of IIT Kharagpur Mechanical Engineering Department, especially after our beloved teachers like Professor A.B. Chattopadhyay, then Professor P.K. Mishra, Professor A.K. Chattopadhyay, and others like Professor Faruqi, who actually shaped up the manufacturing, and many other professors and students also shaped up the manufacturing activity in our department. And today, with the effort of the Advanced Center for Manufacturing, I think this is something that we had been waiting for a long time. So I would like to first begin my talk, and let me share my screen. And I believe I have about 45 minutes. Surjo, is that okay?
Yes, sir. Yeah, absolutely fine.
Okay. Yeah. 1 second. Is my screen visible? Now I will go into the full
It's
screen.
visible. Yeah,
it's visible. Okay, now I could. Yeah, thank you. Yeah, to begin with, I would like to first admit that I am or never been a truly a manufacturing person. I've always been in the field of thermal and fluids, and that's the how things have originated. See, 1 second, my video was coming. Yeah, that's how it had been originated. But we got the opportunity to work on various aspects of manufacturing, which are basically related to thermal engineering and science. So that is what I would like to introduce to everyone. The path that we have taken in the past 2 or 3 decades, and this kind of activity we had started more than 2 decades back. So that's so thanks for giving me the opportunity to share some of those work that we had done earlier. 1 second. Why is the slide? Slide is advancing now. Now, manufacturing processes actually a very vast subject area and is very difficult to define. But in a broad sense, it can be defined as if you start with any kind of raw material and then we do some processing to produce a finished part, we always say that, yes, this is manufacturing. Traditionally, that has been the definition. And there have been, many types of classifications of processes because there are various types of manufacturing processes. Broadly speaking, maybe shaping, joining, and finishing. And under each of these, there are a number of activities that we can list. But this is not the only way to represent the entire world of manufacturing. But many of these activities, we see that there is a thermal aspect, which is a dominant part. So if a heat-driven process is a dominant part of the manufacturing process, which may involve melting, solidification, or any kind of phase transformation, then we can call that thermal manufacturing. And the examples can be casting, welding, laser processing, additive manufacturing, sintering, and many other activities as well. So today, the focus of this talk is on this thermal aspect of manufacturing and the role of process modeling. And I'm going to share with you our experience more than 2 decades back. And especially that's the time when Suman had joined as a master's student, that we tried to explore some of the processes. So there are some case studies that we will share. But before we come to these case studies, we need to recognize that manufacturing or materials processing, to be precise in this case, is an interdisciplinary research area. And we have material science, chemistry, thermal fluids, mechanics of materials, and many other branches of science and engineering which come into the picture. And there are quite a few common thermal, fluid, or transport issues which can involve phase change like melting, solidification, heat and fluid flow, species transport, macro-micro segregation. Then there are interfacial phenomena, shape dynamics, and also the exchanges that happen. Then flow instabilities, non-equilibrium effects. All these actually directly affect the microstructure development and properties, which ultimately show whether the manufacturing process, if there is an integrity in the process or not, whether the desirable properties are achieved or not. But to do that, one needs a clear understanding how these process parameters can control the microstructure development and which will affect the final properties. And what we have tried is a unified approach for the thermal and other phenomena analysis. Then the root of modeling, which is today's theme of the work, theme of the presentation, is to predict the trends and not to, of course, undermine the importance of experiments, not just for model validation, but also to provide some of the insight, especially in manufacturing processes. Those processes can be quite complex, and we may not always, to begin with, understand the complete physics of it. And if we don't understand, we don't even know how to start sometimes. So therefore, modeling becomes an important route along with experiments that we try to understand the physics of it. And then finally, the objective is, of course, to predict the trends, as I have just mentioned. It is never actually possible to very accurately predict in a numerical sense, but if we can understand what causes what, and we are able to design the manufacturing process accordingly, that itself is a great achievement for many of the processes. So some of the case studies I was just mentioning, I'll do. This goes back to more than 2 decades, of course. And that's what Suman was talking about when we started some work on some of these phenomena. One of the examples that I would like to show is the gas metal arc welding process, where we did some modeling, because I'll come to that, those details a bit later. Then laser surface alloying, especially nowadays in the context of additive manufacturing, it is very important, but this is something which we had started even before the terminology additive manufacturing was coined. We kind of indirectly, what we did was precursor to additive manufacturing without even knowing. Then a little bit, some experience we had on laser welding or dissimilar metals. And then finally, I'll talk about our journey in establishing the process called semi-solid manufacturing. So first we will study that GMAW process. Everybody knows about the process because it is a very traditional, welding or joining process, mainly for steel or aluminum. And essentially what it has an electrode, which is a disposable one, which with the arc, it melts and then droplets fall. And with the rest of the heat, there is melting and we form a weld pool. And as the torch is scanned, we get a weldment or a joint over here with a bead. So, but this process again is very complex and has a number of phenomena. So that's why what we started, our approach was to divide the process into various modules. One module would be the electrode analysis, which would ultimately calculate the enthalpy of the molten droplets which would come in. Another module is to calculate the electromagnetic force which would affect the weld pool convection, and it would calculate the current density and finally the Lorentz force. And both these would be combined to do the weld pool modeling, which would have inputs such as current, voltage, torque speed, work peak dimension, etc., along with the thermophysical properties. And we solve the transport equations to get the temperature field, velocity field, weld pool shape and size. Again, this is one of our earlier works. It was published in the early 2000s. First, let's take module 1, electrode analysis. There have been many different types of electrode analysis there, but we tried to adapt something which would fit into our model. That is, we wanted to know what is the enthalpy of the droplets or the rate at which the droplets are falling on the weld pool. So that prediction was first done using electrode analysis. Again, this is a thermophysical analysis that we had done, a CFD modeling of the electrode itself, along with some other physics of arc that goes into it. And then this would generate something like droplet temperature versus current, and we got a healthy trend, which is the higher the current, the higher is the droplet temperature. And as you see there, droplet temperature upward of 2000 degrees is produced. And then what we also found was that about 30% of the total arc energy goes into this protection of the droplets. And then what we do is we now focus our attention on the free surface modeling as the droplets are falling on the pool, how it deforms and how much of this high temperature droplets would influence the temperature distribution inside the weld pool. So that is one way of distributing the heat energy. The other way of distributing the heat energy would be the arc itself. The rest of the heat would go in and be absorbed. But before that, there is a Lorentz force calculation for which we require the solving of the Maxwell's equation. This again, we adapted the CFD modeling technique and use the same kind of code to solve the Maxwell's equation to find out what would be the final Lorentz force field, which would influence the whirlpool convection. So these two models finally fed into the thermal modeling of the whirlpool. And this thermal modeling of the whirlpool, we have the heat source. Other than the droplets falling, we also have to model the rest of the heat that comes in the shape of an arc. And as you see here, there's a kind of a Gaussian distribution of the arc heat, which we model in terms of a Gaussian, the radius of the arc, and then what we get is the heat input. And then finally, we solve all these governing equations in which we not only have the conservation equation, but we also have some sub-models for phase change, which is like melting, solidification, microsegregation, and so on. So these, I will not go into the details. I'll just look at the overall process, overall process modeling of the various multiphysics phenomena. The whirlpool convection, and that was basically the surface tension driven force, which is surface tension is a function of temperature. And remember that we have a very high temperature gradient on the whirlpool surface, and this high temperature gradient can cause a surface tension gradient, and there's a tendency for the liquid to be pulled in the direction of the increasing surface tension, right? And for most metals, pure metals, the surface tension gradient is negative, and so therefore the liquid is pulled in the direction of decreasing temperature, and that is why we get a convection of this nature, because it's decreasing temperature away from the center of the arc. Okay, so that's but how strong connection. So radially outward, yes.
There is a problem in the transmission. It would be good if you switch off your video and then
Okay.
That way improve the.
Okay, thank you. I will just go to the 1 second. Let me.
It will be there at the top.
1 second.
Stop video.
No, I'm just trying to look at my WebEx.
It will be there at the top. If you go top, move the cursor at the top, you will find.
Okay. At the top, it will be.
At the top, you just go toward the end of the screen, then you will find the stop video.
Yes. Okay, thank you. So now I will go back to the PPT, right? How do I go back to my PPT?
Share PPT, share document.
No, that is already sharing.
It is coming up, so otherwise you can just disconnect and then also further connect. That way.
Okay, I'll just stop sharing and share again.
Yeah, that way the situation.
Okay, thank you.
Sometimes it happens.
Okay, are we back now?
Yeah, you are back. Sir, you just put it in the slide mode presentation.
Yeah, it's coming. Already done it. It's coming. Thank you.
It's absolutely fine now.
Okay, I'm just have to minimize this window. Okay. All right. There's still something appearing on the top of my screen. That's why. Anyway, so let me go ahead. Yeah, I think it's vanishing now. Yeah. So here we were. Then especially for steel, there are surface active elements which would alter which can alter the direction of Marangoni convection. Surface active elements like we can have sulfur. So, for instance, if we can have a surface tension decreasing with temperature or surface tension increasing with temperature, then the whirlpool convection will switch. Typically in steel, when there are surface active elements and the surface tension is a function of the surface concentration as well, though it's in parts per million, it can alter. So that is how we get pools of different shapes depending on the content of the sulfur. Even though it's in parts per million, it is because of these curves that would alter the direction of convection. So keeping that in mind, putting all these factors into the models, we do the modeling with the, this is our computational domain with boundary conditions. I will not really go into the details of each and everything, but there are conditions on the surface, there are conditions on the sides, and bottom is insulated and so on. And then finally, just with one slide, I would like to show a representative result, which would give the whirlpool shape and size along with the velocity vectors over there. And it's a transient process. We can catch the process right from the beginning of melting all the way to the full-blown whirlpool, and then the solidification process as well. And then finally, we get, when we study the microstructure and we find the heat affected zone and the weldment zone, there is a good match. Again, it's not a numerical match that we are trying to provide, but at least the trend we can capture as a result of it. Okay, now I would just like to introduce laser surface alloying. This work we had done again more than 2 decades back. That time there was no additive manufacturing, but I would like to bring it in this context because now it has become quite important. Of course, everybody knows about additive manufacturing nowadays, and the object is to to make something not by removing material but by adding material. So we start with, of course, a 3D CAD model, then STL file, and finally there's a printed object that comes out, which is a three-dimensional object of our desired shape and size, and hopefully the desired properties as well. So this is a bottom-up process and layer by layer build-up. And there are many variants of it. Of course, one of them is a metal additive manufacturing based on powder wet fusion is one possibility, or based on powder delivery. So basically powder is melted and then we have a layer of a substance, and like that we can build the material from ground zero all the way to the final shape and size. One of the process, that process of laser powder bed fusion, LPBF process, as you see here, this is one of the most popular processes in which we create a melt pool, and basically we shine the laser, and also either powder is already existing on the substrate, powder of a different material, or we put it in the laser beam to melt the pool. We create a melt pool of that alloyed surface, and then we create an alloyed surface with special properties. So this particular process, as I just mentioned, in fact, Suman was one of the first ones to get to start this activity while he was a master student. So I would like to highlight this part through our activities in laser processing. Now, when we talk about laser, again, before we start modeling the whole thing, we need to understand that laser processing, depends on the type of heat intensity that the laser carries, depending on the kind of focus we have. There are many activities. Laser surface hardening, for instance, is mostly conduction and mass transfer based, where the intensity, the heat flux is not very much. It is only up to about 10 to the power of 4. Then laser welding, it varies. Of course, now we have to melt. So it is basically Marangoni convection driven. And this is the kind of heat flux, 10 to the power of 5 to 7. Then we have laser surface alloying, which we are going to talk about, also has a heat flux of this nature, 10 to the power of 6 on the order. And again, it is very much Marangoni convection and mass transfer driven. And drilling, of course, takes a lot more heat intensity, and there is vaporization and removal of the material. But what we are going to focus now is on this laser surface alloying, which I will describe in a few slides, our experience in this. And again, this is a very old work, which I am reproducing here. Again, what we had done was we have a laser over here, then there's a powder feeder, and as the laser scans, we would produce a clad layer. So our study was only up to this scientific study, and we were not really making a part at that time, thinking one day somebody would coin the word additive manufacturing, but we were just doing it, initial scientific studies of this one. So let's share our experience. The objective was mainly to improve the surface properties at that time. Fluid flow is driven by the Marangoni convection. Then heat, mass, and species transport occurs, because unlike the case of welding, here we are adding another material and alloying. So species transport is an important part of it. We also have a moving heat source, and all these other complexities take place: melting, mixing, solidification. Could be formation of intermetallics, which mechanical engineers, we don't know much about it, but material science experts, they study a lot about this. Final species distribution microstructure depend on all these transport phenomena. Okay. Now, one thing that occurred to us was that when we are having a powder of a material and substrate of another material, the relative melting point of this alloying element and the substrate material should be considered. And why we should consider, I will just share with you. Through our computational model, when we are trying to predict the final macroscopic features of the process and also the species distribution, and the microstructure, this relative melting point also becomes an important point which we had observed for the first time. And how it comes is we go through the computational modeling to understand the basic physics of the process and to predict the outcome based on the process parameters. And of course, the basic computational model framework was the same as the case of welding, except that in the melt pool, the process that is happening is a bit different. So that's why let's focus on that part. And in the governing equation, it is the same. We also want to introduce the species conservation, because we are introducing another species in the melt pool through that powder feeding. Okay. And of course, the top surface is modeled in the same way as far as heat distribution is concerned. So I'm not going to repeat that. So a little bit about the species, because this is a moving pool. On the top surface, we have a species mass input that we have. Because if this m dot is the powder feed rate, then this is how on the top surface, through a species gradient, we would model the rate at which the powder enters. And there is a melting surface as the weld pool is moving in this direction, let's say from right to left. This surface is melting, and this is the solidification surface. Okay. Then what happens is here at the melt surface, we have fresh substrate material flux that comes in. And at the solidification surface, we have, which is the alloying interface, due to microsegregation, we have a flux of the species, the added species, which comes in due to microsegregation, because the solubility of the species is different in liquid than in the solid. So these are modeled in this manner at the solidification front and at the melting front, how the species gets distributed as a species flux. And these are all again factored with the U scan is the speed of the laser movement. Now we do two case studies. One is when we have aluminum and nickel as the base metal, aluminum as a powder and nickel as the base metal. In that case, what happens is, if we look at the aluminum nickel phase diagram, in the case of pure aluminum, the melting is around 600 plus degrees. And when it is pure nickel, the melting is 1455 degrees. Okay. And this is the phase diagram that we have. Of course, these pink lines is basically our linearized phase diagram so that we could put it in our computer model. Then what we notice here is that this lower melting point alignment, in this particular case, the alloying material is lower melting point and the base metal is much higher melting point. And this is the typical, these are the numbers that we have. Sorry, these are the numbers that we have. Now we turn to our model and we produce a whirlpool. These are top view and these are the side view and the cross-sectional view. We look at the whirlpool and this is the depth of the pool and very high Marangoni convection on the top surface. Of course, and then we look at the temperature plots and all, as we see here. This would be these dark lines are the melting points of this is the pure aluminum and this is that of the pure metal, nickel, as we see here, right? So that would define our whirlpool. And then of course the concentration field also we can predict over here. And based on the concentration, we would know at the interface what kind of microsegregation that is happening, and the alloyed material what kind of concentration it has, right? And certain other parametric studies we do, which basically talks about the as the speed of the laser increases, how the depth decreases and how the width can also decrease, because the whirlpool volume actually decreases as the speed, which is predictable, but we just wanted to quantify it with our model, but that is intuitive also. Okay, now we compared with experiments also, looked at the clad layer and looked at the pool in the laser surface alloying. And it's a decent match, I would say, in terms of the depth of the pool. And then what we had predicted was the composition at the interface at the time of segregation. And what we see over here, these circles are the experimental ones. And this is on the x-axis, we have non-dimensional depth. So along the depth, we are just looking at one particular location, what is the normalized composition in terms of aluminum percentage. And this is at a certain speed, at a lower speed. Of course, the whirlpool depth will also be more. And then along the anyway, this is, so that's why this is the non-dimensional depth, so that we normalize it with respect to the depth of the pool. And along the depth from the top to the bottom, we see that these star ones are the computational, the circles are the experimental, and there's a reasonable match as far as the distribution of the species is concerned. And at the higher speed, of course, also there is a good match, but of course the depth is much smaller over there. And the normalized composition of aluminum is also lower, as we see here. Now, If we just reverse it, now if we do a nickel feeding on the aluminum substrate, what we have is the melting point of nickel is much greater than that of aluminum. Now we have an issue. That assumption of a species mass flux, if I just go back and show our model, sorry, this species mass flux is a continuous, as if the species was, it was coming in a molten form over here. Now that is what, that assumption will be violated once we have that the substrate is much lower melting point than that of the powder. What happens is the progressive melting of the particles as they travel in the melt. So therefore now our modeling strategy would have to have, we have to have flow and temperature field in the pool. We need to look at the particle progressively as it melts, as it is transported through the pool, in the pool. So we need a particle melting model. So what we have is, we have an Eulerian model for this, and we have a Lagrangian approach for the module B and C, that is particle tracking and particle melting. Okay. So therefore we have an algorithm which feeds into our basic CFD process. Of course, no standard, CFD code, commercial code can give you this. Of course, this part can be solved, but the other ones, our own model has to be built. So this is the basic strategy that we show. So I will not describe the entire strategy in the flow chart, but what happens is, at the end of it, when we do this process of particle tracking, particle melting, then we have a distributed species mass flux as a source term throughout the weld pool, throughout the melt pool. We have a distributed species source term, and that is very important. Because after we look at the temperature plot, velocity plot, and the concentration field, that is very standard, and of course compare that with some experiments also, the most important part is how does the species distribution now in the solidified pool that we see, a solidified layer that we see. Now here we have this circle are the experimental values, if you see. This is a circle. Again, the same thing, distance from the bottom of the weld pool and normalized composition of nickel in this particular case. So this is the experiment, these circles. Then what we have is, we have two numerical models. One numerical model without the source term modification, that if we assume species mass flux at the top, our original model, then it would have predicted like this, which is complete contrast of what the experiment is showing, these circles. But when we do the source term modification the way I just described, we found a magic that now it predicts it correctly. So that is the power of modeling, process modeling, that can tell us. So that is why, something like additive manufacturing today, we are doing very, very advanced things with additive manufacturing. But if we don't understand the process properly, especially the thermofluids as well as the materials engineering part, the materials part, we will not be able to achieve the final microstructure as well as the composition that we want to achieve. So it is not as simple as just mixing something and producing, and a machine does everything else. So this is what I wanted. So what I'll do is, I spent quite a bit of time now already. I will maybe skip this part, this laser welding of dissimilar materials, but very quickly I just show that okay, I will skip this part and come to the final part of the talk, which is the semi-solid manufacturing. It will take about 10 or 15 minutes, and I think I'll be in time to finish the talk. This semi-solid processing, around 2005 we had started, and we worked for about 10 years on this. Okay, this was originally invented in MIT quite accidentally. That this was it was non-dendritic microstructure was produced by stirring of liquid metal during solidification, and it was identified that because of the dendrite shearing, the dendrites would break away from the roots, and then finally when it is solidified, it would not solidify in this form of this dendritic network, but as non-dendritic microstructure, where we have two phases. One is the primary phase and the secondary phase, which is the near eutectic, the eutectic phase. Now, what happens to this kind of microstructure, as we see here, is it has a thixotropic behavior. If you heat this and then melt the eutectic, then these particles, the primary phase will not be molten because it has higher melting point. So at that kind of state, it would have a thixotropic behavior, basically, which means that it's shear thinning. And then it has the ability to cast into complex shapes with improved mechanical properties, because you will not have solidification, shrinkage, and so on. So this was the property that was identified. And then it was also identified that it will have the potential for lightweighting of aluminum alloys, because you can get much superior mechanical properties with this, with the same composition, and therefore you can do better lightweighting. And then how this stirring is produced, there are many methods. We have done two methods, the electromagnetic stirring and X-cooling slope. Initially, of course, it was mechanical stirring which was done, but you can do more sophisticated work by the electromagnetic stirring, and cooling slope, of course, is a more practical approach. So there are, of course, there are two methods. One is directly, you can have ingot, molten, and then processing, and then finally cast into the parts using this slurry. The other one is a thixocasting process, which is a more elaborate process, which we tried. That is, we first produced the billets having the non-dendritic microstructure. Therefore, what we needed was a DC casting facility with electromagnetic stirring. Then we cut those into certain sizes, remelt using the reheating, or rather reheat, not totally remelt, but reheat up to the semi-solid temperature, and then cast it into parts using a die casting machine. So this is the entire process that we not only modeled, but also did in our laboratory. So that's the experience we would like to share as far as how important modeling is to do something from raw material to a finished product. At every step, how modeling becomes important. The first part is the electromagnetic. Of course, this is the basic science of the thixocasting, that if we do an electromagnetic stirring while it is solidifying, then we would produce this, and then finally this is what I just showed you, that and the reheated billet can be cut like butter, and we actually did it ourselves, and we saw that this is possible. Okay, these steps I just described. So in a cartoon manner, it is just shown over here that these, with the dendritic microstructure, it is then it is reheated using the induction heating, and then in the die casting machine, it is a part can be produced in this manner. And when we produce parts in this manner, it's a near net shape manufacturing that we can achieve. Okay. So, but there are many challenges which are existing in this. The process is sensitive to many process parameters, then lack of understanding of the process, then modeling and the solidification process in presence of electromagnetic stirring. Standardization of slurry production is very difficult to achieve because there are too many variables, and material science is not an easy thing to tackle in terms of its behavior of materials at the elevated temperature and during solidification. Then billet reheating also, we need to precisely heat to a semi-solid temperature. So it's a very small window of success within 2 or 3 degrees sometimes, that we need to heat something at a uniform temperature. And then finally, the die concept, semi-solid die filling and designing a die also we had done accordingly using CFD studies and experiments. Okay. We also needed to study the rheological behavior of the aluminum alloy at the elevated temperature. So that is another separate study which I am not elaborating now. Of course, we start with the model, then Then we did lab scale experiments for low melting point alloys, and we built our own stirrers for aluminum alloys. There are different types of stirrers. Of course, these are rotary plate stirrers, and then these are this is the rotary stirrer, and then this is actually the linear electromagnetic stirrer. And this particular stirrer is what we designed and built for aluminum melting and stirring, aluminum stirring, in fact. So these are just some of the pictures of the various stirrers that we designed. This is CAD modeling, and this is the actual photograph of it. Of course, it is split open over here to show the interior or the anatomy of it. Okay. Okay. So this is, of course, the CFD modeling, but this is the inside the stirrer. We have done CFD modeling, where we have done solution of temperature, solute, solid fraction, and the shear rate, and so on. So what we and in various at various current levels. So this is with 0 amperes, means without any electromagnetic stirring, so only natural convection. And these are the ones with the AM stirring at various current levels that we've seen. So finally, we produce such a billet, and we have some experimentally produced and thermocouples inserted to record the temperatures at various places. And then we compare those time temperature graphs with our CFD model, and we found them to be satisfactory for various current levels. And then we produce a microstructure which is non-dendritic microstructure when we see with stirring of nearly about 450 amperes. And when we do the same experiment without any stirring, we find the usual dendritic microstructure. So that was our first success to produce this kind of stirrer. And then we also, of course, had to experimentally arrange for the process of melting furnace, and then a launder, and then finally a DC casting system. Everything automated in operation, partly automated, I would say. And this is the whole picture CAD model of this we see. So this is the Tundish, and this is the DC casting facility that was developed. Again, as someone mentioned, it was Pramod Kumar, who is now a faculty at IISc. At that time, he was doing PhD. He had done all these things totally by himself, and everything with local vendors, nothing imported. Everything was built in-house, and everything had worked. Okay, so the kind of engineering that was done as a PhD student was amazing. So then we produce this kind of DC cast billets, which had microstructure. This is at the core, and this is near the edge, and this is the edge. So most of the billet across the cross section, we have this non-dendritic microstructure. But how to round off these dendritic ones, especially at the interface, very close to the surface, what happens is solidification is much faster. So therefore, we can produce some dendritic microstructure over there. That is what the induction reheating does to some extent. That induction heating, after induction heating, we see that everywhere across where it's a core or at the edge, we get the non-dendritic microstructure. So now we are in a position to reheat this to a temperature which is at the semi-solid temperature, basically. Use this induction heating. Here also we have done modeling of this induction heating process to arrive at the temperature distribution inside the billet, and then finally choose the right kind of heating mode so that we get near uniform temperature before we put this into the die casting machine. So as we see here, suppose we do the reheating in a single step cycle all the way to the semi-solid temperature, which is nearly about 583 degrees over here. What we see here is, if we expand this one over here, we see between the center and the edge, there is a large temperature difference, which is nearly about 9 degrees, which is not acceptable, because you need the entire billet to be at the same temperature. So what we did was we did modeling, and also according to the model, we altered the experiment and we converted into a 3-step cycle. So heating, soaking, and then heating. And it all took place in a very quick time, only in 11 minutes, as against last time it was, I don't know how much it took time. It was much more than that, I think nearly double time. Within about 11 minutes, we could achieve that uniform temperature between edge and core about 1 degree Celsius. So this is how we get the temperature distribution across the billet. Why we need that is we now need to put it into the die casting machine. Now I will come to that one. Before that, another model also comes into the picture, that is designing of the die by studying the die filling. So if this is the final part that we need to make, and this is the billet that we have, so we have we needed to simulate this process of this heated billet, semi-solid material flowing and then filling up the die space over here to produce the part. So that is what we did. And then of course the viscosity of that, again we did experiments with our viscometer for semi-solid material at that elevated temperature to look at the viscosity, and then we do a curve fitting to come up with a rheological model. And then we run our CFD model. We used Flow 3D software for this, and then finally we got a this is of course the temperature plot. Progressively as the die is filling, we can see over here, and finally this is of course at an intermediate state. The die gets filled finally, and this is the same at the same time frames. We are looking at the solid fraction plots, right? So finally we do a CFD modeling, and then we produce the parts in the die casting machine. Our die casting machine is shown over here, which is a Bueller die casting machine. And then what we see is here are the various, so the journey over here is we start with the electromotive stirring, then billet production. These are schematically shown over here: induction, reheating, die casting, and then final part. That schematic is now produced in reality with the help of our modeling, the same sequence of electromagnetic stirring. Then this is the billet that we have over here. Then this is the induction reheating. Then this is the die that was manufactured, and then finally the finished part that was done, automobile part. So that is, and to proof of the pudding is of course in the material, in the mechanical properties. And what we see here is that when we use the finished part and we do a heat treatment, we find that as per literature, this was the range of so this was the range of yield stress and UTS, and we found our UTS actually exceeded that UTS exceeded what was there in the literature. So we were convinced that the properties were good. Of course, the elongation part, we were at the lower end of it once we did the T6. Of course, before the heat treatment, the elongation was more. But we are still in the range which was predicted, because elongation of course decreases after the heat treatment is done. So that is the end of the talk. I would just like to summarize by saying that the thermal process is the key driver in several advanced manufacturing processes. The objective is to achieve the desired properties of the final product based on the parameters. Understanding the physics of the process is key to the design strategy. Of course, modeling is crucial for just not to better understand and prediction, but also to produce the final part, to design the process. And when we say predicting, we are looking at only the trend part. Again, the prediction, many CFD software companies, they will claim that we can predict any process, up to the, first decimal or second decimal place, we can predict. My suggestion is not to believe any of those. There are many softwares which are available. As long as, these complex processes, the trend is predicted, we should be happy. The rest of it, we should do experiments and then fine tune and come up with the proper process parameters. Okay. So exact matching is too good to be true. So, but understanding the physics is the most important. So as far as the concept to the final product is concerned, it needs both modeling and experiments in a complementary manner. So with that, I would like to, of course, acknowledge for this part of the work that I've just shown, the government has generously supported this activity. Ministry of Mines, DST, DRDO, and of course DST through its wing called TIFAC also supported. And then there are industries also supported our activities in this kind, and as well as basic certification studies supported by General Motors USA. And then we have interaction with various organizations in this activity, TRTTC, that is the, now it's called TCS Pune, I think, CMERI Durgapur, DMRL, ISRO, then IGCAR, and so on. And contribution for this work, almost all my ex-PhD students who graduated up to about 2000 and early 2013, 14, like that. Yeah, many of them worked in this and certification. It was primarily started by Fani Kumar, who is professor at IIT Madras now, and Suman, of course, all of you know. And then many of them are faculty. Pramod is faculty in ISC. Arvind Kumar is now faculty at IIT Kanpur. Neelkant, he was at Jadavpur. I think he has now gone to another institution. Ravindra Pardeshi is now, of course, in TRDDC. That is then Pradip is in IIT Jodhpur. Nirmal is in Kalinga Institute of Technology. Shyam Prasad in IIT Bombay, faculty. Prosenjit in CMERI, and Dipti is in IGCAR. So again, thanks again for the opportunity to share our experience in this field. And I would like to take any questions which may be there. So let me just come out of this presentation mode so that I can. Okay, now let me see. Should I stop sharing or should I?
Yeah, you can share and you can switch on your videos.
Okay, I will stop sharing and switch on my video then, unless I have to go back to any slide. That is very important. Okay, start video. Okay, very nice. Okay, I hope I didn't exceed my time. I don't know.
No, that is absolutely fine. Yeah, absolutely fine. So I'm pretty sure some questions will be coming up from the floor, the floor. Any question? Anybody? A lot of scholars are working in this field, so I assume that some questions will be coming up to their mind. And this is a golden opportunity for them. Scholars in the field of the modeling. Anybody? Any question? One question, I think, was Prakash.
Yeah. Can I ask?
Yeah, please go ahead.
Hello.
Yes, Prakash. Yeah, please.
Okay. Yeah, thank you. Wonderful talk, Professor Datta. I worked with one of your PhD students, Shyam, when we were at Oxford working on synchrotron source with Professor Peter Lee. My background is pretty much on metallurgy and experiments, not much on modeling, but wonderful to see a lot of modeling activities. One quick question, if I can ask you, like in your semi-solid metal processing, especially aluminum alloys, you mentioned that the viscosity of aluminum alloy is measured. I just want to know, like, viscosity is very difficult thing because lots of people measured and there is a 400% of scatter with different measurements. We are also trying to measure this in microgravity space experiments to see under ideal conditions whether we get accurate values. So just I want to know, like, how much of a variation you see in the viscosity of aluminum alloys when you go to semi-solid region, because you may get 10 to 20% of solid grains there. Because in our rheometer, when we were doing under terrestrial conditions, even with oxidation problems, the viscosity is shooting up in the liquid state. So I just want to know your comments about how the viscosity can be considered, like when you go to semi-solid region.
Yeah, I think that's a very important question. See, viscosity of liquid metal as such, it is difficult to measure because it is sensitive to temperature. That's one thing. Now, when it comes to this semi-solid, or when it, as it goes towards the solidus temperature, the sensitivity to temperature is even more. And not only that, when it is in pure liquid form, more or less Newtonian behavior can be assumed for liquid metal. But when it comes to this thixotropic, or rather, I would say semi-solid, when there are particles, then this non-Newtonian behavior starts because the presence of particles. It is very difficult to measure. The reason is that, especially this viscosity measurement work we have done elaborately at in collaboration with CMERI. My ex-student Prasenjit Das is there, and they have done extensive work on this. That is rheological studies. Important thing here is that how to maintain this solid fraction. Suppose you want to, you have the solid fraction, you have shear rate, you have temperature also. I mean, because solid fraction and temperature are related. And then the same solid fraction may be there, but the morphologies of the solid particles may be different. As you hold anything isothermally, the morphologies can change. So these are factors which are very difficult to control. So what we have seen is that more or less, if the solid fraction is maintained at a particular temperature inside the viscometer, then we will get more or less consistent behavior. And we have to vary the shear rate because it's thixotropic behavior, and also sometimes vary the temperature. So we would have to have a mapping of the viscosity as a function of various parameters. Then to get single equation out of it is very difficult because there are more unknowns, and those constants you have to fit by doing various experiments. But as you said, there is a fair degree of uncertainty. But as long as you catch the trend, the rest of it we have to make it up by doing the actual experiments when you're producing a product. So this particular talk, I did not want to focus on those activities, as well as solidification studies, which Shyam Prasad also had done, and many others. Basic solidification studies. I didn't want to touch upon those. I just wanted to focus on the manufacturing process part. But as you rightly said, that it is sensitive. But if the trend is there, no worries. Then the rest of it, you have to actually do the experiments and then work on the parameters to produce the final product.
Thank you. Thank you.
Yeah, just to introduce, Prakash is a faculty member in
Sorry?
the UK.
Yeah, are you?
I'm in University of Warwick.
Okay. Yeah, sure.
In close to Birmingham. Yeah.
Yeah, I know. University. I mean, with WMG there is a good collaboration at IIT Kharagpur.
I am in WMG.
Yeah.
Any other questions from anybody?
Sir, good evening, sir.
Yes.
Sir, in one of these slides, you mentioned that while we are using this electromagnetic stirring, You observed that the core is having no dendritic structure, but the edges contain some dendritic structure.
Yeah, see,
Sir, but actually at the edges, in general the cooling rate is high, right, sir? So we need to get some equiaxial grains over there. So is there any reason, sir, why you have got dendritic structure?
yeah, it's a good question. See, normally, when you are doing any certification of a ingot or let's say a billet, at the edge, the cooling rate is high, so therefore you would get finer microstructure. Maybe not non-dendritic, but at least fine microstructure you will get, which is desirable. But when you are doing stirring to get non-dendritic microstructure, you need the stirring, okay, while it is solidifying. So what happens is when we have the mold, which is filled with the liquid metal and which is being stirred, because the cooling rate at the edge is high, that part solidifies even before it can be stirred. So that solidification happens like any other dendritic solidification. So the rest of it, there is fair amount of stirring and we get non-dendritic. That is the reason. So otherwise, what you said is absolutely right. In normal, without stirring solidification, at the edges you get finer, and not necessarily. Yeah, you can get equiaxed also, but here it's a bit different because we need the stirring.
One question from Professor Kumar S. Kumar of IIT BHU. So he has mentioned that how thin-walled cell 0.5 mm or less aluminium will behave in die casting.
Can you please repeat the question, or is there a chat box where the question can be?
Yeah, it is in the chat box. The question is that how thin-walled cell of 0.5 mm or less aluminium will behave in die casting. That means how critical would be the die casting of aluminium having 0.5 mm or less, the wall thickness.
Oh, okay. Yeah, it's important. See, normally in normal die casting, what happens is if you have thin wall sections, so liquid has to squeeze through that at a very high pressure you are applying. Then when you are doing liquid metal die casting, the more you push, through a thin passage, even if it's millimeter or sub-millimeter, and of course, Professor Suman Chakravarti works on very, narrow confinement liquid movement. But this is not as narrow, but as far as liquid metal is concerned, even something like sub-millimeter, if you push too much, then your pressure drop is quite high and it cannot fill properly because your surface area to the volume flow surface area is much more. That ratio is much more. So there's an enormous amount of pressure drop that happens. So the filling is never proper because the harder you push, the more is the resistance. Then what happens is when it is semi-solid state, it's the other way around. That because it's thixotropic or shear thinning, the harder you push or more shear is there, it becomes thinner. So that's why filling these narrow passages or small gaps is easier when you are having this thin walled section. So that's why semi-solid filling, die filling, thin walled section, you can easily do near net shape. Whereas if it were liquid metal die casting, you would have had to probably live with a thicker section and then machine it later to make it a thinner section. Whereas here you don't have to do as much machining. That's because it's mainly a thixotropic, so shear thinning, so through narrow passage it will flow better.
Is there any other question from anybody? One more question here from Omkar. Omkar. So Omkar, so you can unmute and raise your the question. Put your question.
Sir, this is Omkar from Mechanical Department working under Professor Sujyakantapal.
Yes, Omkar, please go ahead.
Sir, actually my current research work is on friction stir welding. Yeah, means we are focusing on this computational molecular dynamic modeling. How this can be used for the dissimilar material means diffusion, like this kind of work. How far can we can do this kind of work in this friction stir welding?
Yeah. Okay. Let me first admit that I am neither an expert of friction stir welding nor of molecular dynamics simulation, but we had done a little bit of work on friction welding with IGCAR. Well, one of our students did it actually. Friction welding, but friction stir is a bit different, where you have a tool that rotates. When you're doing dissimilar, yes, you can do this, ab initio modeling or molecular dynamic simulation to look at the atomic distribution of the two metals, because at the joint you have two materials, and in friction stir welding you are actually using the tool to make it undergo a plastic deformation, and then the material is distributed in the weldment, okay, physically distributed, and then at the finer scale there is diffusion. So in that sense, molecular diffusion might be all right, and in the final distribution, that is when it is diffusing at the small scale. But before that, the actual stirring of it and physical movement, molecular dynamic simulation, at that scale may be difficult. So you may have to mix the two models. That is, one is the physical transport by the tool movement, and then final distribution with molecular dynamics. This is what on the surface, that's what I feel, that it may not be one model that can suffice, because these are two happening at two completely different scales. That is one thing I feel. And the other thing that happens is, at a macroscopic scale, if you look at the pattern of, I've seen some pictures and I read some papers though, of dissimilar metal welding using friction stir, you will see patterns of chaotic mixing, which is, so that kind of model might also be helpful, because it looks like a turbulence like type of appearance, but because you will never get to that kind of Reynolds number with this friction stir welding, it is most likely chaotic mixing. One can explore that.
Sir, one question from Professor Pradip Saha, I think from IIT Patna, if I'm not wrong. So he has mentioned, like, what is the future of solid state based additive manufacturing over fusion based additive manufacturing?
Okay, I don't think I'm qualified to answer that. I think I will maybe bounce it off to Professor Surjo to answer, because I don't know much detail about the solid state based additive manufacturing. So future, of course, I would say everything has a future. It all depends on what you want to do, because no process is good for all types of materials and all types of products. So there are additive manufacturing as such is a niche activity. It can never replace the mass manufacturing which is done by our traditional methods, in my opinion. So, but to produce parts which are specially made, maybe could be in batch processing or whatever, which cannot easily be made by traditional because till today the microstructural integrity that is required to produce something out of, say, solidification after the additive manufacturing process, that kind of thing has not yet been established, the level at which it is desirable. So we need to be, a lot of work needs to be done. So as a research activity, I think it has a great future. As a manufacturing activity, we don't know. It all depends on the outcome of the research activity. But if you are taking up anything like that in research, I think it should have a great future, any of these.
I think, sir, because of the time constraint, it is almost 9:50. So if any further question is there, so you can write to me, and then we'll consolidate all the questions and send it to sir for further, the clarity or the answers and all. Sir, it was a wonderful lecture, and you have right in the topic, the manufacturing process modeling. You have mentioned about the importance of, the modeling and simulation in manufacturing to capture, the various aspects of manufacturing and all. And you have rightly mentioned, and which I really like, that it is process modeling is not to understand the process only, it is also to describe or define the, the manufacturing strategy, and which you have rightly shown in case of the, the DC casting assembly, 3-step, from your simulation to a 3-step process, so that, the center temperature to the surface temperature difference is just, the minimized from 9 degrees centigrade to 1 degree centigrade. And it was a commendable, the work, research work, I must say, because I am doing experiments, I know how difficult it is, and you have created such a huge setup, the complete setup, and that too, the long years back. So which is a real, but I think the people who are doing research in the field of manufacturing, mostly the experimental work, they will get a lot of inspiration out of this. So, sir, thank you so much for the time and wonderful lecture. I'm pretty sure that the audience have thoroughly enjoyed.
Yep.
And,
thank you, Surya, for the opportunity, and thank you, Suman, again.
Thank you, sir. I mean, it was a great pleasure listening to all these nostalgic feeling. It reminds all those days when we used to have learned on this.
Yes, and thank you for all the audience, everybody, for the nice questions and your participation also.
And next week we do have the the lecture on the smart manufacturing towards Industry 4.0. Our speaker would be the distinguished alumnus, Mr. Ramnath Mani, on April 17th. And then April 24th, we do have the lecture on AI in manufacturing by Professor Manish Kumar of the University of Cincinnati, US. With this, we'll be finishing our the lectures on the month of April, and then already we will have the series of lectures already booked for the month of May as well. So thank you so much for all of your presence. It was really a wonderful lecture, and we look forward to your participation, everybody's participation in the coming lecture. Thank you so much.